Hello. Now I don't need to ask you whether you can hear me. Hey, where did it go? Settle down. So we had some kind of a meeting yesterday, so I think your whatever quiz, test, those dates I think your instructor will put up. Yeah? You're right, he will put up. If he has not already put up, I think he might put it up today. So nothing is surprise. Everything is announced. Yeah? Calm down. That's one thing. Second thing, I am checking. I think they're still in third chapter. They just finished third chapter. I think they're entering fourth chapter. So I think I'll just slow it down because I don't want to go way too ahead. Yeah. Third thing, I forgot to tell you, I've given my username and password to all the tutors for the videos, which means you can ask them and you can make sure we are in sync. Got it? They exactly know what's happening here and they should match. So everybody has got the username and password. I hope you are getting access to the videos. So today I just thought I'll cancel the class, but then I like you guys so much, so I thought let me show up. We'll do a little bit of heat. Let's move on because I don't want to, the rhythm gets a little broken. Let's keep going. So the path function, state function, inexact differentials, exact differentials. So you have the notations, dou. There's a reason why we wrote the work as like this, dou. It's a path function. It's a partial derivative. It's an inexact differential. A total differential of a function is d. That would be point functions or state functions. What energy you have at a given point, it does not care how you got there. So those are state functions. What marks you got does not care how you got the marks. So marks is a state function. The process that you went through are path functions. So let's have some fun. Let's start heat. We all love heat, don't we? Say yes, we are in a hot country. There's no way you can say no. We're going to go with the acronym now, just like the work, HEAT. Go for it, make the acronym work, say whatever you want. H, just like work, but it should encompass most of the things that are related to heat. Think of it a little bit, and anybody is good to go. You can put your hands up and start with H. High vocabulary, low vocabulary, use whatever words you want. Because I got nothing. I did the work. You should do the heat. H, define it. H, horse, huh? Heavy. Hot to cold, is that what you say? Hot. Instead of hot, just get a little more innovative and improvise on it. Hot to cold. Hot to cold. Very good, good start. At least you said the word hot. Hot to cold. E, energy transfer. Very good. Hot to cold, energy transfer. A, for this I'll give you 100,000 points. For A, apple. Hot to cold energy transfer, apple. Apple, application, we'll keep it. Okay, you can write it down if you like application, keep it. But some more essence and meaning of the heat should come about. There is one very important essence of heat that differentiates it from work. That is the hint. That is the hint I'm giving you. There is one essence of heat which makes a clear-cut distinction from work. That's it. That's my hint. You guys have said it previously in earlier classes. You have used the word, you have said it. Even during work, you said it many times. Because that's how you differentiated during the work class also between work and heat. Yeah, go for it. Amount, okay. Amount, quantity is always there. But that doesn't differentiate. Both work and heat have amount. How much? You have already told me this during work class. Little bit you have to think. What is the, so if now in this test and quiz, what if they ask, 1 mark question or 2 mark question? What is the main distinction between heat and work? Because you said all the energies cannot be work and work can be work only if. No. Work is work only if you are. I push this book and this becomes work only if I. Your acronym for O, what did you say? You said organized, you said oriented, to work in unison, to align. At that time I asked you then what would heat be? What did you say? Not anomalous. You said it is random thermal motions. Yes, we went through that. You have random thermal motions as heat. How does that become conduction and do work? Because that energy gets aligned because of the vibration of the atom. Then you get work out of that random heat. So which is random? Work is random or heat is random? That is the main essence. Did you not tell that at that time in the class? Go watch the video again. So go again, hot to cold, energy transfer, wherein the molecules are activated randomly. It is random activation. That's what thermal motion is. Thermal activation is there is no orientation to it. It's like Brownian motion. Everything gets activated, every orientation gets activated, every mode gets activated in the material. It encompasses everything. There is no bias. There is no bias with temperature. Everything gets activated. And it's a random thermal motion. Activated randomly. That is your A. Last T. To equilibrate the temperature difference. Excellent. Now we get it. Very good. hot to cold energy transfer activated randomly to equilibrate temperature difference. Did it put everything inside? Yes? Heat. Okay, so start making the posters. So I'm just going to write this as definition. What is the next thing? Make the boxes. What shall we go next? Huh? Unit. Okay, we'll go with it. Unit. I wonder what it is. Anyway, you pay for electricity, so I think you should know the units. What's the units? What is thermodynamics about? First class. What's thermodynamics about? Like finance. Tracking of energy. Tracking of energy. So what's the units of energy? Heat, joules, whatever you want, joules, calories. If it is specific energy, joules per mass, kg. Units next box. I'll go with whatever you want. Yeah. Okay, go with mode. Okay. Shoot off. What are the three modes? Okay, give me an example for conduction. Huh? Heat transfer. Through a rod. I burnt my hand today. I was making some toast. I wonder what mode that is. I touched the pan and I burned my hand. Burned my finger. Huh? Conduction. Sure? Very sure. It's not miracle. So would I have made contact? Okay. So if I made contact, what is the mechanism of, because you're calling this as conduction, then what's the mechanism? Is it a contact mechanism? Then convection is not a contact mechanism. So conduction is a contact mechanism. Yes? Does it depend on something to contact, such as a medium? Yes, okay. Then does convection depend on a medium to make contact? Yes, okay. Then what's the difference between conduction and convection? Huh? Movement of what? Medium, movement of medium. I don't understand what's movement of medium. You said both cases there is contact and there is a medium which makes contact and which transfers heat. Yes. Then what is the difference between conduction, contact and transfer, and convection, contact and transfer? Okay. They translate. Translation transfer is convection. Predominantly vibration transfer is conduction. But in metals slightly something else. It's not exactly vibration in metals. There is also conduction because of electron transfer. There is also conduction because of electron transfer. Now that could be also translation because the electrons are actually delocalized. Yes. So they are translating the electrons, but the atoms and molecules are not delocalized. What is the third one? So you said contact is required, medium is required, so only then you will have transfer. So conduction, I burnt my finger. Convection? Example. Air. Oh, wonderful. So you're feeling the hot air, huh? Then how you know it's air? If you don't feel the hot air, how you know it's air? Oh, you're feeling the cold air. Okay, you're feeling some air. Okay, or hot air or cold air. So you're feeling it. Okay. Why do you call it as convection? Because it's translating, it's moving, it's circulating a lot. circulating a lot. We use fans to do what? No, what is the thought process there? Are you thinking of conduction or are you thinking of convection? What is the objective of fan? The fan makers, what is their objective? To make you feel uncomfortable. No? To make you feel comfortable. How? If they simply circulate air, that won't make you comfortable. Which sometimes a fan does make you uncomfortable. If you didn't know. What is the objective of fan? You said it's convection, so then I would assume that it is used for transferring heat. Yes? How does it transfer heat? Because you are the one who brought up the air example. See, I didn't do it. I'm going with whatever you are going with. She said air. She feels the cold air. So what strikes your mind when you talk about air, cold air, hot air? Fan. So how is fan a heat sink? How is it making you feel comfortable? Oh Jesus, we went to the pressure part. We don't think too much of the pressure there. How does fan transfer the heat? Towards it. How it knows what is hot air towards it? It does not have a thermostat control. If you know that the fan does not come with a thermostat, it does not have a mind of its own. All it does is a turbine going round, round, round. That's it, the blades. It does not know that it has to identify hot and suck it in. It doesn't know that. Nor does it suck in, because when you stand in front of the fan, I don't think you feel sucking feeling. You feel blast on your face. It's emanating more than sucking. Stand next to a fan. How does fan do the business? Because you are saying convection. Thank you for the example. How does fan remove heat or reduce the local heat in order to make you comfortable? Then I will understand that you understand convection. Because you gave me a very wonderful definition, right? You said conduction is local vibration of atoms. Convection means it's translating. I'm just checking whether translating is translating to the real world product. I think I just answered the question. Is translation translating to the real world product? Did I answer the question? How is fan? What is fan doing? What is it doing to air molecules? It's translating it. It is pushing it. So while pushing, what happens? Does the dispersion increase or does the dispersion decrease? Increase. So there is an optimal rate of dispersion and good amount of dispersion throughout your room that should happen. What happens when you, like a madman, simply increase the speed of the fan? It goes counterintuitive. What happens after a while? The dispersion is so high and the energy is so high, they start to collide, and what do you feel? Hot. You start to feel hot. So I hope you know how to use a fan now. You need optimal amount of dispersion, but it should not be so much that they should start colliding and start giving you heat. So all of you know, when you sit under a fan after a while, discomfort. It's hot. Because they're now very nicely they're transferring that heat. They're not dispersing the heat, they're transferring the heat, and that heat's back again to your place. So we have convection and we have forced convection. So when you turn on a fan, you're also providing momentum and you're forcing some more convection. But if you force it so much, that the friction will increase and it will dissipate heat and you will feel the heat again. So no use. The whole function of fan gone. So what was I asking about? I just wanted to see, since you said translation, I wanted to see what translation does in a real room. It disperses things. Yes? It disperses. Radiation? Radiation? I thought you said conduction, convection, radiation. What's radiation? Huh? It's mass coming at you, huh? Radiation is mass coming at you? No, mass is not coming at you. Momentum is coming at you? Who said no? Obviously, without momentum, there is no energy. Yeah, there's mass, there's momentum, energy. So momentum is coming at you? Yes. Then is it doing work and energy is coming at you? Yes. Does it require contact? But does it require transfer? Yes. Example, radiation. What? Sunlight, okay. I was just wondering, you'll give me some fancy example of radiation. Sunlight. Now give me a fancy example. Oh, very nice. How you know? Huh? How you know it's radiation? You said microwave, he said microwave. I'll agree with him, but I am not, up here. So, I just want to learn from him. How do you know that microwave is providing energy? You just answer that question. I didn't ask about mechanism, I didn't ask about modes. How do you know microwave is radiating? How do you know? Oh, food gets hot. Sure? Okay. So you're not making contact heating there? Are you sure? Is there not hot air that is circulating there? There's no convection there? Very sure? Okay. That's how you know that it's neither conduction and convection, so you go by elimination, it has to be something else. It has to be the third thing. Radiation. But that's exactly not how it gets heated. That energy does not come and heat up your food, if you didn't know. That's not exactly how microwave heating happens. It's not like sunlight. You keep something in sunlight and directly the electromagnetic beams, waves, came and got your food molecules to get excited, and then it got it to de-excite and got heated up. It didn't happen that way. Yeah, it doesn't exactly heat the water molecules. The water molecules themselves generate heat because of your microwave. The water molecules themselves generate heat. You are not supplying any heat. All you are supplying is a stimulus of certain frequency with your microwave. What does the water molecules in your food tend to do? They tend to polarize. They tend to polarize. You have a lot of hydroxyl groups in your water, right? They tend to polarize to your oscillating electrical signals. What happens? They cannot move at that frequency and polarize. So what happens to all the energy when they're trying? They rub against each other. What happens? You get internal molecular friction. That is what heats up your water. That's exactly what heats up your water. So there is no direct heating. Like, what is direct heating? Does the conduction create direct heating? Because conduction means it should conduct and it should move away from the place outside, then that should cool off, right? So for something to become hot at a place, what should happen? For the heat to come in, there should be conduction. I got it. At the boundary, for the heat to come in, there should be conduction, or there should be convection, or there should be radiation. But for that heat to stay there, what should happen in your material? Otherwise, it will keep going. In which case free electrons? Metal. No, but the metal, if you heat from one side, it's out, it's back to air on the other side. The electrons will carry it and send it out through the rod, through the thickness, through the length of the rod. It's out that way. So now you told me wonderful things of how heat can be transferred, but how will you hold it at a plate? So first you have to get the heat into your bucket. For that you use conduction, convection or radiation. But how will you hold it in the bucket? Because if it's an open bucket, it will keep going out. So you will say you have to close the bucket. How do you close the bucket? What do you want in the material to do? Obviously you need to insulate. You need to insulate and trap the heat, otherwise the heat won't get trapped. Or you should look for materials that have high what? High which thermodynamic property? I'm just already moving on to another most important property in your thermodynamics or in your life. What would that be? Loudly tell me, what would that be? Heat capacity. Heat capacity. Capacity to hold heat. So it's not enough that you just get the heat inside. Yes, you have to hold it. You have to hold it. Very good. Modes. Next box. What shall we go? Exo, endo, I don't think you need to do. Exo is giving out, endo is taking in. Sign convention, endo positive, exo negative. Work sign convention, system doing work, like you running positive, you getting run negative. You running positive, you getting pushed negative. Got it? Yeah. Use simple examples, yeah? You are the system. You are the system. Next box. So don't make a box for endo exo. That's pretty straightforward. Don't want. How about you give me types of work? How can you generate work? Heat. Heat generation. What are the different ways? Since you now said heat. I will start off. Fan by collisions, forced convection. See, my example is over. I'm like broken record player. I use the same thing. Fan can also generate heat. So what would that heat be? Friction. So don't say friction, I used it up. Sorry. Friction. That's my example. Now your turn. Wait, hold on. Somebody else? Louder. Boiling anything? Hold on. Can you repeat again? Burning. Pyrolysis. Flame. Pyrolysis. Burning. You need fuel, you need oxygen. Burning. Pyrolysis will work. You will get flames, and flames will have different intensities of heat, depending on which flame it is. Next. Excellent. Who said that? I wonder how that goes. Okay. Yes. Why that filament is emitting heat? There's a filament inside, right? That filament's also giving out heat. You're right about that. Obviously the bulb is hot at times. Don't touch it. Why is it emitting heat? Very good. Resistance. If you have resistance, you will get friction. You will get scattered. Scattered will give you heat. What is the fancy name for this? Resistance heating or Joule heating. Joule heating. You put resistive elements and you pass electric current, you will get heat. So this is like the blocking. You remember last class I said blocking and allowing. This is blocking. If you block something, you will get heat and pressure will increase. Yes, it's blocking. You are resisting. Very good. Electric. You didn't tell me something little more, usually students will tell that, little more simpler way of generating. Okay, so pyrolysis, friction, electric, what else? Nuclear, huh? No? No, I'm not talking about the forms of the energy. I'm talking about how you generate it. So you can generate it by friction, and that friction can be kinetic or can be potential. The electron can be potential or kinetic. So I'm talking about generating. How do you generate? So she said pyrolysis, I said friction, somebody else said electric. What else? Huh? Deformation of what? Is it coming from complete deformation or is it coming from rubbing, from friction? So automotive tires are usually hot, very hot. Is that coming from the fact that they're bouncing off of the road, or is it because of friction? Because they're not really they're deforming temporarily, but they're recovering, right? So what is getting created there? What is getting created? They deform, recover, deform, recover, deform, recover. And heat is getting generated. Why? Why? You brought up a very good example. You bounce the ball a few times, or you take a rubber band and you do this a few times and put it on your lips, you will burn your lips. I guarantee you that. Don't do it. Next class, don't come with burnt lips. It will happen. So at least you know that heat is coming out. That you know. So I just went a little bit further and asking, why is heat getting dissipated? No, if it were elastic, it wouldn't release, you see. If it were elastic, the meaning of elastic is whatever is given, come back to the original position. So it's the friend of elastic who doesn't do that. There is a viscous element there in your rubber band. The elastic would have taken everything and given it back, so it will go back and forth, but it doesn't happen like this. There is a viscous element. The viscous element will provide friction and it will dissipate heat because it cannot move as fast as you're doing this. So viscous element. So if it's a rubber ball also, it's not perfectly elastic. It will have a viscous element. So it will damp on the floor, and it will give heat. It will get converted to heat. That's why it's damping. The elasticity is becoming more viscous. Very good. So viscous heating, pyrolysis heating, friction heating, viscous heating, electric heating. Next. Still there is one simple thing that you have left off. I mean, I say simple because I think you should know that. Huh? Exo? Oh, finally. Finally somebody short of chemical reaction. Yes. Chemical reaction. Usually that shows up first. Chemical reaction. Chemical heating. Yes, because due to reaction. What else? What else are we missing? Anything else? Did this cover everything? Oh, there's one more. There's one more. It need not always be chemical reaction. There could be some physical phenomena that might also give heat. That's my hint to you. It need not always be an ionic bond or a metallic bond or a covalent bond that is forming. It can be some physical event that could also give out heat. Say that again. Who is that? Fission. Oh, you went to the but that's, we'll put that in nuclear. That's why I mumbled nuclear, right? We'll leave it in nuclear reactions. We'll leave it in chemical reactions. Give me a physical phenomena. We have already talked about this already a lot. That's my hint to you. Phase state, phase change. Very good. Phase transition. Excellent. That is the latest trend in heat technology. Phase change materials. This is the latest thing in green technology right now. How to encapsulate phase change materials in construction materials and walls so that they act as thermostats. Or in food safety, to keep the food at a proper temperature, because food is very sensitive to temperature. Phase change materials. Very good. You just took me right into PCM. Yeah, it's an exciting field. So these phase change materials are reversible. Why are they reversible? If something gets too hot, it will hit their melting point. So they will act like a heat sink, take the heat, and maintain the temperature. And then when your outside cools off, they also cool off and again become a solid. Solid to liquid, liquid to solid. Or liquid to vapor, vapor to liquid. So they can go million cycles, reversible, back and forth, back and forth. And these are usually green materials. They're very safe organic molecules. So they're green. They're green and they're reversible. They have a very high shelf life. So you can go how many ever times. It will give you the same enthalpy of taking the heat and then the same enthalpy of giving out. Yeah. How in phase transition there is dissipation? Need not be, right? How is it dissipating? So the entire phenomena should be used only for, sorry, the entire heat should only be used for changing the phase. But if it's used for any translation or any collision, then you will have dissipation. So how should you go when you are doing the phase change? Very slow. Typically that's the idea. But on this side of melting and vaporization, it already goes quasi, because the kinetic events are less. When you come from the other side, there is a lot of translation and kinetic events. Kinetic events, so answer to your question is, if it's equilibrium, if it's thermodynamics, dissipation will be less. If it's translating and if kinetic events are predominant, you will have dissipation. Can you sum it up now? Instead of looking at me, write down all the heats, because I think you gave me very good examples. What I like was a viscous heating example. Very good. If we have left out anything, you can pile on. Phase change heating is also there, chemical reaction, electric, microwave. How do we measure heat? Shall I put one box saying measure? I didn't ask you about work. How do you measure work? How do you measure heat? When was the last time you measured work? You could have easily measured work if you go to one place regularly. Louder. GYM, okay. How do you measure work there? So which machine? Elliptical, treadmill, rowing, which one? Elliptical, okay, let's go with elliptical. How do you measure work there? It will, some sensor will come and touch you and will, okay. How does it measure work there? cycles and resistance and the diameter of the flywheel. Yes. How many times the flywheel rotates, what's the diameter, and what's the force that's being applied? Did you get Newton meter there? Okay. Ergometers, those are work meters. Ergo. All your treadmills, everything, all the machines in gym have ergometers. How about heat? Louder. Okay, I have no idea, but I think your word makes sense. Calorie meter, count the calorie meter. And I have no idea what it means. I mean, I don't know how it works, but I think I have an idea of what you mean. Calorie meter. How it measures calories, how you can measure calories. He said it very nicely. Sounds exciting, right? Calorie meter, calorimetry, calorimeter. How, see, work is easy. You can take the pedal, you can know what is the radius or diameter of your rotation, you know what load you are applying, you get the torque, you get the number of cycles, you got it. You got your wattage. Work is over. How do you measure heat? Calorimeter is fine, but how do you measure heat? This has to be 200,000 points on it. How can you measure heat? Between what and what? Huh? Hold on. Measuring device and substance will tell you what. So let's say substance gives out heat and the measuring device's temperature will change. Correct? How do you know how much heat it is? No, delta T I got it. But how do you know how much of that delta T is related to Q? That will work? Yeah. Joules per gram per degree Kelvin. Yeah. Everything. You have to take mass and unit change in temperature. You should know the temperature difference. So the better way to do it is you keep your sample, you keep a reference. Then an event happens in your sample. The delta T will change. And your reference should be pumping heat or removing heat to keep the same temperature between the two. Then you know how much you're supplying and how much you're pumping. Get it? The principle of delta T between reference and sample to be 0. If you maintain the same temperature between sample and reference, exothermic, will it heat up or cool up? Heat up. Then you know what you should be doing on this side. Endothermic, heat up or cool up? Cool down. So you know what you should be doing. You will get your Q. Calorimeter works on the principle of having a reference and a sample and trying to maintain the same temperature between the sample and the reference. That is how you will know how much heat it is giving out, how much heat it is taking in. Because you are doing the same thing on the reference side. Oh, very good. Calorimetry, yeah, nice. We have a very good calorimeter in the campus. If you guys are taking some chemistry courses, you can go to Central Analytical Lab. There is a calorimeter there. You literally can measure wattage for all the events of phase transition and everything else. Chemical reactions, phase transitions, you can do it. Central Analytical Lab, CAL, Chemistry Department. Work and heat, is it just a permanent thing, or is it a property, or is it a process? Is it a property or is it a process? It's a process. It's a transient process that happens. Where do you usually experience it? First, say, how do you know that heating or cooling is a process? How do you know it's a process? How do you know it's a transient process? And when do you know actually it's a process? Okay, hint to you is open the door. That is my hint. So what do you do to open the door? What do you do to open the door? What happens? What is cold and what is hot? Metal is cold, metal is hot. Hand is cold, hand is hot. Then what happens? What's your experience there? At the boundary point, what happens? Your hand starts to feel cold after a while. That is the process. That's why it's a process. It's not a property. It's a process that happens over a certain time. That is how you feel it. And what you said is even better. It will always be felt at the boundary. At the boundary. So you should know how to identify the boundary. So I did shoulder press the other day, right? So the boundary is shoulder press, the weights are coming up. Where is the boundary? Between me and the rope and the weights on the other side. That's the boundary. That's where you can actually see it moving, the rope. Yes? If you don't find a boundary, you cannot experience heat and work. You have to find the boundary. And it's a transient process. It's a process. It's not exactly a property. I think that's all I had. Is it a state function or a path function? I just said it's a process. It's a path function. Anything that's a process is a path function. Shall we split? Catch you guys Tuesday.